one of the examples that's in your book. It's on page 748. I will note that on here. So this is, yeah, coming to us from page 748. And it goes a little something like this. So we have our, oh, that's awfully big. We have our force that's being applied on a lever. And you can see the lever here is oriented in the ZY plane. And the force is a vertical force of 50 pounds applied at the end of this lever. And I guess we need to add here that the lever itself is 1 foot long. So this is a 1 foot long lever. And so what we're going to do is do a cross product of these two vectors. The vector PQ is the torque arm, and the vector F, which is our force. And what will happen when we cross product PQ with F, we're going to get the moment of the force around the point Q, sorry, or point P. Getting a little distracted here with a little keen-eyed visitor over here. Keeps coming in. She's very insistent. So anyway, so first things first, what I want to do is actually vectorize this quantity here, PQ. And so I'm going to, kind of put in a vector here for us. Oh, that's an unfortunate color. It doesn't show it very well, but I guess you can probably make it out okay. And so the vector PQ, we want it in IJK form. The I vector, remember, is along the x-axis, and so obviously this is 0 i's. But we need to know how far out it is in terms of the j vector, and then how far up it is in terms of the k vector. And you've probably noticed we have ourselves a little triangle here. And so we're going to use a little right triangle trigonometry to come up with the other two sides of this triangle. We know the hypotenuse is 1. We know this is a 60-degree angle. That means we know this is a 30-degree angle. And there we have our 30, 60, 90. So this has to be 1/2. And this has to be square root of 3 over 2. So our PQ vector then can be written as the sum 0i plus 1/2 j vector plus square root of 3 over 2 k vector. Now the F vector, because it's straight down, is actually a pretty easy vector. You notice it doesn't have an I component. It doesn't have a j component. But it does have a k component. Whoa. Sorry. It's got a negative 50 k. It's negative because it's in the downward direction, of course. And so in order to come up with the moment for the torque, I'm going to do the cross product of these two vectors. And so let me write that out here. So the way you want to do this, you want to take the torque vector, which is PQ, first, and cross product that with the force vector. And that will be the moment. And it is going to be a vector quantity. Now, if I reverse the direction of multiplication, what it does is it reverses the direction of the moment, but you want to do the torque arm cross product with the vector. So to do this, of course, we're going to do our, oh boy, I should just draw them quicker, and then I wouldn't have that problem. Whoops. So PQ is going to be first, and then so that's 0, 1/2 root 3 over 2, and then 0, 0, negative 50 for F. And let's see, I seem to remember last time I did a reduction by minors, and I told you it wouldn't matter. So I guess I will do the diagonals method, since there are some folks who like that method. So I'll just copy over my um, two columns. I hope that shows up okay for you guys. It's a little hard for me to read on the gray screen, but anyway, I sure hope that works for you guys. And here's what's interesting about this particular cross product. When I multiply in my diagonal lines, try something a little broader stroke here, like this. Notice that the j and k vectors, the product is going to be 0. That's also going to be true going this direction. So really, there's only one vector quantity here that didn't zero itself out in that. So you can see that we've got an I times 1/2 times negative 50. So we get a negative 25I. And then there's 0 J's and 0 K's. So this is the moment of the torque about the point P. Notice it's just on the x-axis, going straight in to the paper. So that's what, it's perpendicular to these two vectors because it's perpendicular to the YZ plane. Yeah, so the torque is actually into the, oh, that was so creepy. Sorry. So anyway, that's a great example of a torque problem and how the cross product allows us to figure out what direction the torque will be when we use this lever in this particular force. So there's one example of how we could do a problem that involves the cross product and is a little bit more of an application. The other one that we're going to see is using the triple scalar product. So it's a scalar multiplication. What it is when we have a parallelepiped, which is like a prism, but it's at an angle maybe. It doesn't have to be at an angle. It could be at an angle. You can actually find the volume of the figure if you vectorize 3 of the edges that all meet at one of the corners. And so the example that we're going to do is from page 749. So I'm going to save this, I think. Oh, good. Screen save. There we go. And I'm going to take us to our next problem. So let me clear this off and take us to our next problem. Here it is. So for our next application, we're going to show you how something called the triple scalar product will find the volume of something called a parallelepiped. So think of a parallelepiped like a prism with a parallelogram base at an angle. They don't have to be at an angle; they could be straight up and down. But if they're at an angle, the triple scalar product will work regardless. And so the idea is to use the triple scalar product, which you will see on the bottom of page 748. The triple scalar product is saying, look, it's a scalar, so we're not getting a vector quantity now. And it says, look, if you want to do this particular multiplication of the dot product of u with the cross product of these other two vectors, you can actually show that the 3x3 matrix that we would normally use can be adapted so that it's really just finding the determinant of this particular matrix. Because remember, the matrix determinant is a scalar quantity unless there's variables in the matrix. Like when we did this cross product before, we had I, J, and K across the top. Now what I'm saying is, like, look, if you're going to dot product this thing anyway, why not do it all at once? You can throw the other vector on the top row of the matrix, and it will give you the scalar, which is the volume of the parallelepiped. I guess I should be careful here because depending on the order that you cross product those, sometimes they turn out negative. And so it's the absolute value of this thing that will give us the volume. So if I wrote it like this, I'd say the volume of this figure is the absolute value of u vector dotted with v vector cross product w vector, like so. So just the absolute value, because I don't remember with this particular problem how it turns out. I know it says down here the volume is 36. I don't remember if it get positive or negative 36 when we do it in this order, but we're going to do it in this order. So that's what we'll do. We'll just plug these together real quickly here. So u vector, you can see, is 3, -5, 1. 3, -5, 1. V vector is 0, 2, -2. 0, 2, -2. And W vector is 3, 1, 1. So this cross product will be the bottom two rows. And then remember, then we would take our U1 times the I coefficient for the cross product. Then I would take our U2, which is -5, times the cross product for the J coefficient. And our U3, which would be our K coefficient, times the K coefficient for the cross product vector, and then we just add them all together anyway, which is exactly what the matrix is going to do. So it's actually pretty cool that this whole thing works out the way it does. I'm going to do, we did diagonals last time, so we do minors this time. It doesn't matter what row we choose to go down. I guess most of the time we'll just do the top row. Oh, that's my timer. I had set a timer for 15 minutes, but I screwed up the previous one so bad. I'm editing that bit out. So it was I was trying to rush too fast, and so I didn't do a very good job. So this is going much better so far. So the 3 is a positive because it's in row 1, column 1. 1 + 1 is 2. The -5 is in row 1, position 2. So it's going to get a negative. Now it's already negative, so you can already see what's going to happen there. And its minor is 0, -2, 3, and 1. I'm going to run out of room here, so I'm going to write this on the bottom, just below it here. We know that the minor for +1 is a positive because it's in row 1, position 3. So 1 + 3 is 4. And it's a 1, so I'm not even going to write it in there. I'm just going to put the minor down. 0, 2, 3, 1. So let's evaluate these minors. This is 3 times 2 minus -2. This is -5, so +5, times 0 minus -6, plus this is 1 times 0 minus 6. And so we end up with, let's see, 3 times 4, 12, 5 times 6, 30, minus 6, sure enough, 42 minus 6 is 36, just like they said right there. So I guess we did get the positive 36 answer. No need to have the absolute value signs there. So that's something called the triple scalar product. It's another cool application of the cross product. And in the case of the volume of a parallelepiped, it's a nice geometric application for something that seems pretty high level, but in reality, cross product is just something you haven't seen before. Or maybe you had. I'm not sure. For those of you who've been in physics, if you had seen the cross product when you were doing torque problem. So, all right. Well, that's it for your second day of work on cross product. Hopefully, these videos will help you. And yeah, if you have any questions, please feel free to shoot me an email. Comment. Like and subscribe down below. I'm kidding. Don't do that. I hope everybody has a great Thursday and a great 4-day weekend. Yeah, again, if you have questions, feel free to email, but we're not going to Zoom unless we desperately need to if there's something terribly wrong. So, all right, everybody, have a wonderful Thursday. Hopefully you're all doing well and staying healthy out there, and I will talk to you next week. All right, I'll post some new lessons videos for you on Tuesday. So have a great day, everybody.